So today we're going to talk about instantaneous velocity. So the first thing we can do is give a general definition, which would be the rate of change of position of an object at a specific point in time. This concept can be better described analytically. So we have Vx equal to lim as delta t goes to 0 of delta x over delta t. So breaking this equation down, Vx is just equal to the instantaneous x velocity. So this is if the velocity was going in the x direction. And then we have delta t equal to the change in time, and then delta x representing the change in position. And then lim as delta t goes to 0 is just the limit as the change in time goes to 0. So essentially what this expression means is that we're making the time interval infinitesimally small to yield the instantaneous velocity. So as we continue to shrink this time interval, it will become so small that it'll just be the velocity at that moment. Hence, it will yield the instantaneous velocity. So we can look at this also from a calculus interpretation. So we have the instantaneous velocity in the x direction equal to the limit as the change in time goes to 0 as the change position over the change in time. And in calculus, this is the definition of the derivative of x with respect to time. So that's what we write on the right-hand side here. Now, a couple of notes just to remember with the instantaneous velocity, the change in time is always going to be positive. So that's just one important thing to note. Also, if the instantaneous change in velocity is positive, this means that the position is increasing and the motion is in the positive x direction. Now, I thought it also might be useful to go over an example. So let's say that the equation below models the motion of an object. X equals 4 plus 6t squared, where t is time and x is position. And let's just say it wants us to find the instantaneous velocity at 5 seconds. So the first step, we should write down our givens. So they give us the equation x equals 4 plus 6t squared, and they give us time equal to 5 seconds. And then the next thing we need to do is to identify what we need to solve for, and we're solving for the instantaneous velocity. And the equation we're going to need is Vx equal to dx over dt. This is the equation we need because they gave us a equation for the position. If they just gave us points, we can use the other definition we had for the instantaneous velocity, but since they gave us an equation, we have to use the calculus version. So we can start by rewriting the equation a little differently. Vx equal d over dt, and then isolate for x. And then from there, we can plug in the equation they give us for x, so it'd be 4 plus 6t squared. And then we can rewrite it as the following, just to make it simpler. So the derivative of 4 is going to be 0, because we know that a derivative of any constant is just 0. So that just leaves us with a derivative of 6t squared. And just a side note, remembering how to do this derivative. So generally, the derivative of x to the power of c, where c is a constant and x is a variable, to do this derivative, you have to bring c down and then subtract 1 from c. So now we can apply this to our example. So we have to bring the 2 down and then subtract 1 from 2. So we'll get 12t for our answer. But we're not actually done yet. We have to find the instantaneous velocity at 5 seconds. This is just the general equation. So we can plug 5 seconds in for it, and we get 12 times 5 equal to 60 meters per second, and that will be our answer.